The National Electrical Code, or NEC, provides guidance on calculating voltage drop through a fine print note, or FPN, under Section 215.3. However, this note is not an enforceable requirement. The authority having jurisdiction, or OJ, determines whether voltage drop calculations are mandatory. The FPN does not specify which current value to use for I in the voltage drop equation. Section 230.31 states that service lateral conductors shall have sufficient ampacity to carry the current for the calculated load. Therefore, the calculated load of the dwelling should be used for I. While the voltage drop FPN is not directly enforceable, AHJ may adopt it as a local requirement or use it as a basis for decisions on electrical installations. Where voltage drop calculations are required, the AHJ may specify the acceptable voltage drop limit and calculation methods. There are several reasons why the NEC uses an FPN instead of making voltage drop calculations mandatory. Firstly, voltage drop calculations can be complex and time-consuming, especially for large electrical systems, making mandatory application impractical. Secondly, voltage drop varies significantly based on factors such as cable length, material, and operating conditions. Flexibility in the recommendation allows for consideration of site-specific conditions. Thirdly, excessive voltage drop can compromise equipment performance and pose safety hazards. Strict voltage drop requirements can increase installation costs. The FPN provides guidance while allowing flexibility to balance safety concerns with economic factors. The NEC voltage drop FPN is a recommendation for electrical professionals to consider voltage drop when sizing conductors. While not directly enforceable, AHJ may adopt it or use it to guide decisions. The current value to use for I should be the calculated load of the dwelling. The equation you mentioned, voltage drop equals 2 times L times R times I divided by 1000, is a common formula for calculating voltage drop in a two-wire circuit, where voltage drop is the voltage drop in volts, L is the one-way length of the conductor in feet, R is the conductor resistance in ohms per 1000 feet, and I is the current in amps. Understanding each component is essential for accurate calculations. The length, L, must be the one-way distance from the source to the load. Using the total loop length will result in an incorrect voltage drop calculation. The resistance R is typically found in NEC Chapter 9, Table 8 for conductors. The table provides resistance values in ohms per 1000 feet at a specific temperature, usually 75 degrees Celsius. For conductors not listed, or when operating at different temperatures, adjustments to the resistance value may be necessary. The current I is the most debated part, as you pointed out. The NEC doesn't explicitly state which current to use in the voltage drop calculation. However, the intent is to ensure that the conductors can handle the load they are expected to carry without excessive voltage drop. Using the calculated load of the dwelling aligns with this intent, as it represents the maximum demand expected under normal operating conditions. Now let's discuss the AHJ role in more detail. The AHJ has the authority to interpret and enforce the NEC within their jurisdiction. They can adopt stricter requirements or clarify ambiguities in the code. While the voltage drop FPN is not mandatory, the AHJ can make it a requirement based on local conditions or specific project needs. If the AHJ requires voltage drop calculations, they may also specify the acceptable voltage drop limit. The NEC recommends a maximum voltage drop of 3% for branch circuits and 5% for feeders. However, the AHJ can set different limits based on the type of installation or equipment being served. Additionally, the AHJ may specify the methods used to calculate voltage drop. While the formula you provided is common, other methods, such as using voltage drop calculators or software, may also be acceptable. The NEC uses FPN to provide guidance and recommendations without making them mandatory requirements. This approach allows for flexibility and considers the diverse range of electrical installations. Mandating voltage drop calculations for every installation could be overly burdensome and impractical. Not all installations require the same level of precision in voltage drop control. For example, A short branch circuit serving a lighting load may not be as critical as a long feeder supplying sensitive electronic equipment. Voltage drop is influenced by various factors, including conductor length, size, material, and temperature. Site-specific conditions play a significant role in determining the actual voltage drop. By using an FPN, the NEC allows designers and installers to consider these factors and apply appropriate voltage drop calculations based on the specific installation. Maintaining a balance between safety and cost is crucial in electrical installations. Overly strict voltage drop requirements can lead to increased conductor sizes, which can significantly increase material and labor costs. The FPN allows for a more flexible approach, where voltage drop is considered in conjunction with other factors such as conductor ampacity, overcurrent protection, and equipment requirements. To perform accurate voltage drop calculations, it is important to consider several factors. Firstly, use the correct conductor resistance value. Table 8 in Chapter 9 of the NEC provides resistance values for various conductor types and sizes. Ensure that you use the appropriate resistance value for the conductor being used in the installation. Secondly, account for temperature correction. Conductor resistance increases with temperature. If the conductor is operating at a temperature higher than the value used in Table 8, you must apply a temperature correction factor. The NEC provides guidance on temperature correction factors in Table 310.15b. Thirdly, consider reactance for alternating current, or AC circuits. In AC circuits, reactance can contribute to voltage drop, especially in long conductors. Reactance is caused by the inductance and capacitance of the conductor. For long conductors, it may be necessary to include reactance in the voltage drop calculation. The NEC provides information on reactance values in Chapter 9. Fourthly, use appropriate software and tools. Voltage drop calculators and software can simplify the calculation process and improve accuracy. These tools often include built-in databases of conductor properties and can automatically perform temperature corrections and reactance calculations. Fifthly, document your calculations. Keep a record of all voltage drop calculations, including the assumptions made and the values used. This documentation can be helpful for future reference and can also be used to demonstrate compliance with the NEC and any local requirements. The FPN on voltage drop is located in Section 215.2a of the NEC. It is important to note that this is a fine print note and not a mandatory requirement. The FPN recommends that voltage drop be limited to 3% for branch circuits and 5% for feeders. The NEC does not provide a specific formula for calculating voltage drop. However, the formula you mentioned is commonly used. The NEC does provide guidance on how to calculate conductor resistance in Chapter 9. The NEC also provides guidance on how to calculate conductor ampacity in Section 310.15. The AHA has the authority to determine whether voltage drop calculations are required for a particular installation. The AHA may also specify the acceptable voltage drop limit. If the AHA requires voltage drop calculations, it is important to follow their guidelines and use the methods they specify. Voltage drop can have a significant impact on the performance of electrical equipment. Excessive voltage drop can cause equipment to operate inefficiently or even fail. It is important to consider voltage drop when designing and installing electrical systems to ensure that equipment operates properly. The NEC provides guidance on how to minimize voltage drop. Firstly, use conductors of sufficient size. Larger conductors have lower resistance and will result in less voltage drop. Secondly, keep conductor runs as short as possible. Shorter conductor runs will result in less voltage drop. Thirdly, use conductors with low resistance. Copper conductors have lower resistance than aluminum conductors and will result in less voltage drop. Fourthly, minimize the number of connections. Each connection adds resistance and will increase voltage drop. Fifthly, ensure that all connections are tight and clean. Loose or corroded connections will increase resistance and voltage drop. To summarize, the NEC voltage drop FPN is a recommendation, not a mandatory requirement. The AHJ determines whether voltage drop calculations are required. The calculated load of the dwelling should be used for in the voltage drop equation. The NEC uses an FPN to allow for flexibility and consider site-specific conditions. Accurate voltage drop calculations require consideration of conductor resistance, temperature correction, reactance, and appropriate tools. By understanding these factors, electrical professionals can effectively manage voltage drop and ensure safe and efficient electrical installations. Always consult the latest edition of the NEC and local regulations for specific requirements and guidance. Remember that the information provided here is for educational purposes and should not be considered a substitute for professional engineering advice.